In this program, we will be discussing sculpture. What exactly? A few basic techniques, a restorer's workshop, and 2 leading-edge technologies. The origins of sculpture go back to the sense of the sacred. Does the Bible not say that God modeled Adam from clay? And was the passion of Pygmalion, the sculptor of Greek mythology, not fulfilled when the goddess Aphrodite brought to life the ravishing statue he had carved? The myths, like some sculpting techniques, have come down through the ages. The art of sculpture allows the artist to give shape to a memory, an observation, or an abstract idea. To achieve this, the artist employs highly concrete techniques. One consists of carving a material. Bit by bit, the sculptor removes fragments from a block of stone, wood, or other material. With this technique, his every move has a definite effect, since any mistake is irreparable. Unlike carving, modeling lets the sculptor change his creation constantly. The sculptor models by adding little portions of material, removing the excess, and so on. Only materials having a certain plasticity, such as moist clay, plaster, hot wax, and mortar, lend themselves to this process. Once he has completed his work, the sculptor can reproduce it in one or several copies by casting it in bronze. The bronze alloy founders use today is mainly composed of copper. In its pure state, copper has the disadvantage of being extremely soft. Indeed, its atoms are arranged in regular patterns, forming a network of superimposed layers. When stress is applied on that structure, the layers of atoms have a tendency to slip over each other. The ease with which the atoms slide over each other is the result of small dislocations between the rows of atoms. Adding tin to the copper remedies this drawback. The tin atoms, larger than those of the copper, settle in the dislocations in the atomic network. The alloy thus obtained is much harder than pure copper. However, copper has another drawback. It has a tendency to oxidize, meaning it will combine with oxygen, which turns it a blue-green color. This problem is overcome by adding zinc to the copper. Zinc deoxidizes the copper and improves its resistance. Bronze also contains traces of lead, which makes it more malleable and facilitates the finishing processes. The most common process for casting a bronze statue is called lost wax casting. The first step consists of covering the sculpture with a liquid rubber called elastomer. In a sense, the elastomer forms an impression of the sculpture. When dry, it is removed from the model and encased in a frame to keep it in place. Next, a heat-resistant cement is poured into the elastomer mold. This core reproduces the exact shape of the sculpture. When the cement forming the mold is dry, the mold is opened, the core is taken out, and a layer a few millimeters thick is scraped off. In the next step, the elastomer mold is closed over the cement core again. Wax is then poured into the cavity between the mold and the core. The sculptor founder checks the wax and reshapes it according to the original work. Its surface is then covered in a network of canals, also made of wax. It is through this network that the molten metal is carried into the hollow area between the mold and the core. The founder then finishes molding the piece. He does this by smearing several layers of heat-resistant earth over it. The piece is then left to dry by ventilation for about 2 weeks. The piece is then gradually heated to melt the wax, which escapes through the network of canals. After the piece has been fired for several days, the founder buries it in a pit filled with steel filings or earth. He then pours the molten bronze into a funnel connected to the network of canals. The molten metal streams through the canals and fills the space between the core and the cast. 24 to 48 hours later, the cast is broken and the core withdrawn. The sculpture, a hollow replica of the original, finally emerges. But it needs finishing. The final touches are the chiseling and the patina. The sculptor chisels away all surface imperfections and brings out the details of the original. The patina will give the bronze a particular sheen and color. The sculptor has his pick of colors ranging from red-brown to dark gray, from green to blue. The patina is obtained by applying several coats of certain chemical compounds, such as acids and oxides. When heated with a blowtorch, these compounds color the surface of the bronze. Unlike styles of sculpture which have evolved through the ages, the basic techniques of sculpting have remained much the same. This is probably because they have always met the sculptor's standards.
Whether they be figurative or abstract, sculptures have to face the passage of time, precipitations, pollution, natural deterioration. All are destructive agents. The restoration workshop is where they are rejuvenated to their original splendor.
Although generally made of highly resistant materials, sculptures nonetheless fall victim to the passage of time. A number of situations, like exposure to the outdoors and bad weather, will accelerate the aging process. A sculpture's worst enemies are water and freezing. Water in the form of rain or snow dissolves the salts contained in the material. Moreover, it infiltrates minute cracks in the stone. When it freezes, the water expands, causing the stone to shatter. Also, air pollution makes rainwater more acid. Acid rain attacks limestone with a vengeance. Indeed, it changes it into calcium sulfite, a weak black solid. In addition, constant humidity causes the soluble salts in the stone to migrate toward the surface of the sculpture. Once evaporated, these salts crystallize and gather dust to form an unsightly layer of black scale. The process used to rejuvenate a sculpture varies according to its material and degree of deterioration. A common procedure used to dislodge dirt encrusted on sculptures is nebulization. It consists of spraying the work with a mist of hard water, that is, calcareous water. Hard water is preferred over soft or demineralized water because the latter might dissolve the salts some stones are made of. The mist is sprayed over the sculpture for several days. The water does not damage the stone, but soaks the dirt thoroughly and helps to dislodge it. There is another, gentler way to restore sculptures that are particularly fragile. It is an ammonium soda chemical process. The restorer dissolves this chemical salt in water to make a paste. He impregnates cellulose compresses with the paste and applies them to the surface of the sculpture, where they soak up the dirt without affecting the stone. Badly damaged sculptures covered in layers of black scale are generally dry cleaned by fine sandblasting. In a pressurized stream no larger than the nib of a pen, a very fine abrasive powder is sprayed directly onto the scales to be removed. The powder usually consists of minute glass beads that shatter on contact with the stone. The effect on the statue is less harsh, not like a real abrasion, but more like the rubbing of an eraser. To remove tougher crusts, corundum powder is used. Corundum is an extremely hard mineral occurring in gem varieties such as ruby and sapphire. For hardness, it is second only to diamond and therefore has a more penetrating abrasive effect than the glass beads. However, when a sculpture requires more delicate treatment, gentler abrasives are used, such as an apricot pit powder or crushed ears of corn powder. These substances are harsh enough to dislodge the dirt without damaging the stone. Today, restorers have access to a tool that effects an even more powerful and accurate cleaning: ultrasound. Dentists use this technique to remove tartar from the surface of teeth. Restorers use ultrasound to treat sculptures having concretions, that is, deposits of crystallized salts or calculus. These deposits are typically left by runoffs that pick up salts when they go through soil. Concretions will build up on the surfaces of sculptures that remain buried in the ground for long periods of time. Although these deposits can be as hard as marble, ultrasound will reduce them to powder, and its high precision is an invaluable asset. Whatever technique the restorer chooses, he is guided by three principles. The first is to preserve as much as possible of the original work. The second is to make the restorations reversible whenever possible, by using a soluble glue, for example, to mend a broken sculpture. Should the missing fragment ever be found, the restored piece could be unstuck and replaced with the original. The third principle dictates that restorations remain discernible. In other words, we should be able to see restored parts, and this is done out of respect for the work and for the viewer. Before beginning any restoration work, the expert has to make a choice. He may, on the one hand, choose to restore the work in a way respectful of its history and without concealing the mutilations it has suffered over the years. On the other hand, he may choose to restore the sculpture to its original splendor by subjecting it to a draconian cleaning. He may even reconstruct the missing parts, in which case restoration becomes more than the application of certain techniques, but an art in itself.
The preservation of our artistic heritage is vital, but it is just as vital to enrich it. Modern technology offers sculptors new tools to work with. Let me introduce you to two of them.
The boom in scientific knowledge and technological know-how has opened up a whole new range of possibilities to the artist. While traditionally sculptors create motionless works, fixed in space, today some are animating their sculptures thanks to remarkable and revolutionary materials called shape memory alloys. These alloys have the ability to memorize one or several shapes, to which they return when exposed to certain temperatures. Before being discovered in certain metal alloys, this shape memory phenomenon had been observed in plastics, certain fabrics, and even hair. However, in shape memory alloys, it can be controlled. For example, a straight wire can be made to memorize the shape of a clover. The artist first bends the wire to give it the shape he wants. He then heats it to a given temperature, while forcing it to keep its new shape. Reaching this critical temperature triggers a memory process as yet little understood. The metal then memorizes the atomic arrangement of the clover shape it was given. The metal is then cooled and springs back to its original shape, that of a straight wire. If this process is carried out often enough, the metal will eventually learn to remember the shape the artist gave it. It will automatically resume the clover shape whenever it is heated to the memorization temperature. There are two types of shape memory. Objects with single shape memory will only memorize one shape. However, the same alloy, subjected to a different process, will memorize a whole series of shapes fashioned by the sculptor. This is called double memory effect. This process enables sculptors to create exterior works that change shape in response to changes in temperature. Some will move with the hours of the day, others according to the seasons. It all depends on the choice of the memorization temperature and the proportions of the compounds in the alloy. At present, the best alloys displaying this property are mainly composed of nickel and titanium. They have a memory of 100,000 cycles, meaning they can reconstruct a learned series of shapes 100,000 times. After that, they become amnesic. Their memory can also be erased simply by heating the work beyond the memorization temperature. In addition to the discovery of these materials whose properties are almost magical, sculpture has also benefited from new designing techniques. Stereolithography, for example, enables the artist to create three-dimensional objects without using his hands. The process is amazingly accurate and rapid. A highly complex object can be sculpted in a matter of hours. Stereolithography uses certain plastics, which will solidify when exposed to the ultraviolet light of a laser. The sculptor begins by sketching his ideas down on paper. Then, using computer-assisted design, he can draw his object in 3 dimensions and change its volume as he sees fit. Once the exact shape of the object has been determined, its digital image is relayed to a stereolithography device. This machine consists of a container filled with a liquid resin which is kept at a steady level. A tray that moves up and down bathes in the liquid. A laser beam irradiates a well-defined area of the resin covering the tray. This hardens a layer of resin, which will be the first layer of the object. After this initial laser scan, the tray carrying this first layer is sent down into the resin, then back up and scraped. As a result of this operation, a thin layer of liquid resin covers the hardened layer. This process is repeated until the object is completed. Stereolithography has applications in many other fields, including medicine and industry. For example, based on an image of a patient's bone taken by medical imaging techniques, the experts are able to reproduce a three-dimensional replica of that bone. This kind of reproduction can be used to design prostheses perfectly suited to a patient's anatomy. It was long believed that art and science were opposites. Today it appears nothing could be further from the truth, since science continues to open up new possibilities to the creative genius of artists.
Sculptures will soon shed their age-old immobility to take on lives of their own. And divine intervention will have had nothing to do with it, only sheer human genius.